Today we have Pradeep Rai, who is at present Inspire Fellow, right? Inspire faculty at HRI, and he did PhD at HRI with Manoj, uh, and he's going to talk about Schur multiplier of prime power graph groups. Pradeep.
Okay. Thanks, sir. Uh, okay, so I shall be speaking about Schur multiplier of prime power groups. Uh, why are we interested in Schur multiplier? So, suppose we are interested in constructing a prime power group, that is a group of order p to the power n for some prime p and some natural number n, as a central extension of a group of order p to the power n minus 1. Of course, I mean, if a group of order p to the power n is given, it can be realized as a central extension of a group of order p to the power n, because the center is non-trivial. Choose the central subgroup of order p, and then you have such a short exact sequence. But suppose we want to start from a group of order p to the power n minus 1 and construct a group of order p to the power n as a central extension. So Schur multiplier gives an idea that how many such groups can be constructed. Okay, so how Schur multiplier comes into a picture. So suppose a central extension of this kind is given. Choose a section S from G to E, so that each G belongs to G, has a unique coset representative SG. So that is G equals to S of Gn. So SG denotes the representatives of the cosets of n in E. The next line in the calculation just says that the element S of G1, G2 lies in the same coset as S of G1 into S of G2, right? And therefore, we have an element in N, let's say that CG1, G2, such that S of G1, G2 equals to CG1, G2, S of G1 into S of G2. So this process gives us a map C from G cross G to N. Now, one can verify that this C is a two cocycle. What does that mean? So let G be a finite group, and let A be any abelian multiplicative group. Take the set of all those functions f from G cross G to A, such that f of xy equals to f of xyz equals to f of yz into fxyz for all xyz in G. So such functions are called two cocycles. And let us denote this set as Z2GA, and then take the set of, so okay, so such functions which, okay, I said that already, which satisfy this property are called two cocycle. Now let's take those functions from G cross G to A, for which there exists a function T from G to A, such that fxy can be written as Ty into Txy inverse into Tx. Then such functions are called two co-boundaries, and this subset makes a subgroup of Z2GA. And when we take the quotient, that is called second cohomology group of G with coefficients in A, considering the trivial action of G on A. Okay. So as I said, given any central extension, this gives an element of the second cohomology group, H2GN. Now suppose an element of the second cohomology is given, that is, suppose we start with a two cocycle, that gives us a central extension of G by N in this manner. So you take the Cartesian product G cross N, and then define the binary operation as G1 N1 into G2 N2 equals to G1 G2 and this is N1, N2, C, G1, G2. So that makes G cross N group, and moreover a central extension of G by N. So this gives us a correspondence between the central extensions of G by N and the second cohomology group of the second cohomology group H2GN. So this says, the theorem says that the equivalence classes of extension of G by N are in bijection with the elements of the second cohomology group H2GN. Okay, so in this way, H2GN gives us an idea that and how many groups at most can there be constructed from a group of order p to the power n minus 1 as a central extension. Now I have still not defined what is Schur multiplier. So the second cohomology group with coefficients in C star is called Schur multiplier, and we shall denote it by Mg. And there is a relation between H2GC star and H2GA for any finite abelian group. So that's this. Let A be a finite abelian group, then H2GA is isomorphic to G by G dash tensor A, direct product Mg tensor A. Okay, so this says that if we have an idea of Mg, then we have an idea of H2GN, and then about the central extensions. So that shows that why these things are important while investigating about the prime power groups. Now going back in the history of the subject, am I audible? Hello, Anupam sir? Hello?
Yes, yes. Yeah.
Okay. Okay. So let's go back a little bit into history of the object. So it was Issai Schur who was studying projective representations of finite groups when these multipliers just popped up. So what is projective representation? Let G be a finite group. Any ordinary representation of G over C is a group homomorphism from G to the general linear group GLNC. And any projective representation of G over C is a group homomorphism from G to the projective general linear group, that is the central quotient of the general linear group. Now, of course, if an ordinary representation is given, there is a homomorphism from G to GLNC given, you can compose it with the natural map from GLNC to PGLNC and to get a homomorphism from G to the projective general linear group. The Schur was trying to investigate this question, that can we always lift a projective representation of G to an ordinary representation of G? That is, given any projective representation of G, can this projective representation can be found in this way, that by composing with an ordinary representation, composing natural map with an ordinary representation. By an easy example, one can see that this is not always possible. Take an identity map from PGLNC to PGLNC. Instead, what Schur discovered, that there is another group G star such that every projective representation of G can be lifted to an ordinary representation of G star in some sense. So let's see what Schur discovered. So he proved that Mg is a finite abelian group for a finite group G, and he showed the existence of a covering group G star. So what is a covering group G star? A group G star is said to be a covering group of G if G star has a subgroup A such that A is contained into the intersection of the center of G star and the commutator subgroup of G star. And this A is isomorphic to the Schur multiplier of G. And when we quotient out G star by A, this it gives us G. So in some sense, studying the projective representation of G to study the projective representation of G, it's good enough to study the ordinary representation of G star. So in what sense? So suppose a projective representation of G is given, then it can be lifted to an ordinary representation of G star in this sense, that such that this so if a projective representation of G is given, there exists an ordinary representation of G such that this diagram commutes, right? So this pi is just the natural quotient map, both sides. Okay, so in this sense, it's good enough to study the ordinary representation of the covering group. One can see that if your Schur multiplier is trivial, then A is trivial and your G star is nothing but A. So then every projective representation can be lifted to an ordinary representation of G itself. Right? So Schur multiplier comes in as an obstruction this way. Okay, how Schur multiplier appears while studying projective representations? Somewhat in the same idea as I explained in the beginning. So suppose a group homomorphism from G to PGLNC is given. It's a projective representation. Then let for every G belongs to G, LG be a coset representative of P of G in GLNC. That is P of G equals to LG ZGLNC. Right?
Pradeep, somebody has a question.
Yes.
Somebody has a question probably.
Okay.
Somebody raised hand. I don't know who raised hand.
Sorry, sir, by mistake.
Okay, no problem.
No problem. Okay, so P of G equals to LG ZGLNC. Then again PGH equals to PGPH, and this gives us a map from G cross G to ZGLNC again, but ZGLNC is nothing but C star, so this gives us a 2 cocycles. So that way, I mean, while studying projective representations, Schur multiplier comes. Of course, I'm not going to prove what Schur discovered. So let's go further. What else Schur discovered? So why to be interested in P groups? So it was discovered by Schur only that if P be a silo P subgroup of a group G, then the Pth part of Mg, that is silo P subgroup of Mg, lies inside the Schur multiplier of silo P subgroup. Okay, so having knowledge over the Schur multiplier of silo P subgroup gives us a hand in investigating the Schur multiplier of the groups itself. What else Schur discovered? He also explicitly determined the Schur multiplier of abelian groups. So suppose any abelian group G is given, it's written as Zn1 cross Zn2 cross Znk, such that Ni divides Ni minus 1. Then the Schur multiplier is given by Zn2 cross Zn3 square. Zn3 square is the direct product Zn3 cross Zn3, and so on, up to Znk to the power k minus 1. And this follows from a more general fact, which was also discovered by Schur. So he proved that the Schur multiplier of the direct product G1 cross G2 is isomorphic to the Schur multiplier of G1, direct product with Schur multiplier of G2, direct product with G1 tensor G2. Here, this just means the tensor product of abelianizations of G1 and G2. Okay. Okay. So what are the main problems on Schur multiplier of prime power groups? So as listed by Moravec in a talk at Group St. Andrews, these are the main problems. So the first one is the classification of the groups G with trivial Schur multiplier, and then finding bounds for the exponent of the Schur multiplier, and finding bounds for the rank of the Schur multiplier, and bounds for the order of the Schur multiplier, and in which abelian groups occur as the Schur multiplier of non-abelian groups. In particular, a problem from Kuroka notebook, which says that, is it true that every finite abelian P group is isomorphic to the Schur multiplier of some non-abelian finite P group? Right? Okay, so there's already been a talk by Professor Prasad in this group theory Sangam series only on the first problem, that is classification of groups G with trivial Schur multiplier, and already been a talk on the second problem, that is bounds for the exponent of Mg, and by Professor Thomas. I shall be speaking on the bounds for the order of the Schur multiplier. Okay. So
Siddharth, your question?
Yeah, Pradeep, I just wanted to ask something.
okay.
Yeah, so the previous slide, when you talk about the conjecture about the bounds, you mean the bounds, how the bound grows with respect to the log of the order of the group? So, I mean, it could be unbounded above, right? So,
have we talked about bounds?
yeah, so this conjecture in the next slide, yeah. So bounds for the rank of Mg, how do you know it is bounded? Is there some evidence? I mean,
Yes, yes. I shall be giving an evidence that bound of the rank of the Schur multiplier is bounded into terms of the rank of the group. Actually.
Okay. So there is some constraint on the group. I mean, something like log of the order or something.
Yes.
I mean, that's the most naive thing I can think of. Yeah. Okay. Thanks.
Okay. So let's talk about the bounds on the order of the Schur multiplier. So where did it begin? So it was Green who gave a bound for the Schur multiplier in terms of the order of the group. So he was investigating this problem, which is known as Scott's conjecture, so which says that there exists a function f from n to n such that for each h belongs to n and each prime p, if G is any finite group, such that p to the power f of h divides mod G, then p to the power h divides mod odd G. So this was conjectured in 40s or 50s, I'm sorry, I don't remember. And then it was proved by Lederman and Newman. And the function was improved to a quadratic polynomial by Green's using the bound on the Schur multiplier of a group G. It's still open in the sense that people wonder whether this function can be improved to a linear polynomial function. Okay, coming to our bound, so Green proved that if order of G equals to p to the power n, then order of the Schur. Hello, yes.
I think this is the right time to mention that the exposition on this conjecture is covered in a book.
Yes, sir. So I'm sorry not to be taking audience attention to the book. So there recently a book has come out by Professor Pasi, Professor Manoj, and Professor Mahendra, which takes this conjecture and talks about it a complete chapter is devoted to this thing. I think it's chapter 3. So one can look into that chapter if one is interested in having a further knowledge about the topic. Okay. So okay. So yeah. So it was Green's bound, which says that mod g equals to p to the power n, then mod mg is less than or equal to p to the power half n into n minus 1. Why Vigold gave the same bound using a different approach while he was trying to get a bound on the commutator subgroup of a group G in terms of the order of the central quotient. And one can see that the bound is attained for all elementary abelian P groups. That is the direct product of cyclic P groups. Okay. Okay. So since the bound is attained, we can't say that they were improved, but they were of course refined later, considering different terms such as the number of generators of G that we shall denote by D of G, or the number of minimal number of generators of the central quotient, or the order of the derived subgroup. So Gashers et al. In 1967 gave this bound, which says that if the order of mg is less than or equal to order of mgab, that is the abelianization of the group G, into mod gamma 2g to the power d of g by zg minus 1. So of course, as the Schur multiplier of abelian groups can be determined, one can use this theorem to obtain the Green's bound. So this is more general. The bound of Gashers was further generalized by Varmani in 1969. He proved that mod mg is less than or equal to mod mg by gamma cg. So gamma cg is the cth term in the lower central series, where C is the nilpotency class of the group G. Okay, into mod of G by gamma 2g tensor gamma cg by mod gamma cg. And one can derive the Gashers bound by Varmani's bound. One just needs to apply the same bound to mg by gamma cg. So just put G by in the right hand side, put instead of G, put G by gamma Cg, and keep iterating the process, and one will reach at the Gashers bound. This bound of Varmani was reproved by Jones again in 1974. Using some different methods. There is another long list of the bounds, but going further in more number of bounds, I think this is an appropriate time to give an idea that how such bounds can be achieved. Right? So we will derive the bounds of Varmani actually. Not by the method of Varmani actually. Okay, so let's what works here while investigating about the order of the Schur multiplier are the exact sequences. So it was proved by Schur only that if G is a finite group given by F by R for a free group F, then Mg is isomorphic to F dash intersection R over Fr. So that's the description given by Schur himself. And using this description, many exact sequences can be constructed, and which shall be very helpful for the investigation of the order business. So let's see one of the sequences proved by Blackburn and Evans, which has been very helpful, at least in my investigations. So if G is given by F by R and N is a normal subgroup of G such that N is isomorphic to SR by R for a normal subgroup S in F, then we have an exact sequence, this thing. So one going into R intersection Fs upon Fr intersection Fs going to mg, then going to mg by n, going to g dash intersection n, by commutator ng going into 1. Of course, as the description of mg is available in terms of f and r, one can expect such an exact sequence. So it suffices to give an exact sequence of this kind. So the first term is the same as in the last one, r intersection fs by fr intersection fs. Then write mg as f dash intersection r over fr. Then g by n. So since n is sr by r, g by n can be given by f by sr. So this thing is f dash intersection sr by fsr. And then one can see that n intersection g dash by ng comes out to be isomorphic to f dash r intersection sr over fsr. And if you look closely, there are natural maps between these terms, which gives the exactness of the sequence. Okay, now concentrating on the sequence of the Blackburn, you see on the left side is still the description is in terms of f and r, which we want to replace in terms of g actually. So not here, not in general. Okay, let's see a corollary first. So when in this sequence n is replaced by gamma cg, gamma cg is the cth term in the lower central series of G, where C is the nilpotency class. Then you see S is given by gamma CF. So the first term is R intersection F gamma CF, that is gamma C plus 1F. That gives us gamma C plus 1F, that is intersection R. Of course, if F by R is nilpotency class of C, that gamma C plus 1F is in R. So that gives us gamma C plus 1F here. Again, FR intersection FS, this FS is again gamma C plus 1F, so that gives us gamma C plus 1F intersection FR to MG by gamma CG to gamma CG to 1. So it's just N is replaced by gamma CG. So now we have an exact sequence of this thing, this kind, and now we want to replace the leftmost term in terms of G. How one can do that? So this is actually the leftmost term, gamma C plus 1F upon FR intersection gamma C plus 1F is a homomorphic image of G by gamma 2G tensor gamma CG. So let's see this. This is not a corollary. I'm sorry to be. Okay, so let G be a finite nilpotent group of class C, and let G is given by F by R. Then upon identifying G by gamma 2G with F by gamma 2FR, so of course, when you write G as F by R and gamma 2G as gamma 2FR by R, you can identify G by gamma 2G with F by gamma 2FR, and gamma CG with gamma CFR by R. Then the natural map from G by gamma 2G tensor gamma CG to this thing given by F gamma 2FR tensor XR going to the commutator FX FR intersection gamma C plus 1F. This is a well-defined map, and this comes out to be a surjective homomorphism. So you consider the kernel of this map and denoted by X, then we can replace this term gamma C plus 1F upon FR intersection gamma C plus 1F by these two terms. So one going to X to G by gamma 2G tensor gamma CG to MG by gamma CG to gamma CG to 1. Okay, now everything is in G only, and using the exactness of this sequence, you see this MG by gamma CG GG can be taken down. So okay, I mean, using the exactness of this sequence, when you look closely, one gets this thing, that is the bound of Vermani, except mod x. So mod mg is less than or equal to mod mg by gamma cg into mod g by gamma 2g tensor gamma cg upon mod gamma cg. One just needs to look close on this exact sequence to find out this thing. And so it gives us some actually extra term x, which occurs at each step. Yeah. But if you don't take x into account at all, this gives us a Vermani's bound. So we have an upper hand when we have such an x, and actually the investigation of this x provides us with even more refinements of the existing bounds on the order of the Schur multiplier. So a list of further bounds. Okay. Let G be a finite P group of order P to the power n with mod gamma 2G equals to P to the power K. And then it was proved by Viegold that mod Mg is less than or equal to P to the power half D minus 1 into 2n minus D. This was later improved by Ellis and Viegold in 1999 as not improved, but it's a refined that mod mg is less than or equal to p to the power half d minus 1 into n plus k. Of course, it's not obvious that this is a refinement. So you see this 2n minus d can be written as n plus n minus d. So when you compare the term n minus d and k, you see n minus d is always less than or equal to k for a finite P group.
Sorry, Pradeep.
Yeah.
This D is the rank you're looking at here?
Yes. Sorry, this D is the minimum number of
generators. Okay.
Minimum number of G. I'm sorry not to be mentioning it. Okay. Okay. So that's the bound, and that's how it's a refinement. And the bound is attained for the homocyclic P groups. Okay, some more bounds. So let G be a finite P group of order P to the power n with the order of the derived subgroup is P power K. Then mod of Mg is less than or equal to P to the power half n into n minus 1 minus K. So in terms of the order of the group and the order of the Schur multiplier. This was again improved by Vermani, who showed that mod mg is less than or equal to p to the power half n minus k into n plus k minus 1 minus k. So this also can be written as p to the power half n into n minus 1 minus half k into k minus 1 minus k. So he improved it by the term half k into k minus 1, comparing to the Jones bound. Actually, his bound follows from a more general bound he proved, that if the restriction homomorphism from mg to mk for a central subgroup k is 0, note that for a cyclic central subgroup k it is always 0, then mod gamma 2g into mod mg is less than or equal to mod g by k abelianization tensor product with k into p to the power half m minus r into m plus r minus 1, where m and r are given by mod g by k into p equals to p to the power m, and r is given by mod gamma 2g k by k equals to p to the power r. So the second bound follows from this thing. Okay. This was further improved by Nirumad for non-abelian P groups G. So for non-abelian P groups G in 2009, he proved that mod Mg is less than or equal to p to the power half n minus k minus 1 into n plus k minus 2 plus 1. So one can look at it as this. So p to the power half n minus 1 into n minus 2 minus half k into k minus 1 plus 1. And so in the second description, one can see that it improves the earlier bounds, which are given in terms of the order of the Schur multiplier and order of the derived subgroup for non-abelian P groups G. Okay. Some other bounds in terms of the co-class of the group. So the co-class of a finite P group is defined as this. So suppose the nilpotency class of the group is C and the order of the group is P to the power n, then n minus C is called the co-class of the group. And Moravec proved in 2011 that this mod mg is less than or equal to p to the power r square plus k plus 2 into r. Okay, a group of co-class 1 is called the group of maximal class, and Moravec also proved for groups of maximal class and n is strictly greater than p plus 1 that mod mg is less than or equal to p to the power p plus 1 by 2 into the ceiling of n minus 1 upon p minus 1. So mod mg is close to the square root of mod g actually. Okay. Some improvement, not improvement, again refinement. So let G be a non-abelian finite P group of order P to the power n with mod gamma 2G equals to P to the power K and D of G equals to D. Then a mod Mg is less than or equal to P to the power half D minus 1 into n plus K minus 2 plus 1. I'm sorry if I am boring you with all those so many number of bounds, but it's this way only. Okay, so one can see that this is a refinement, because in earlier bound of Nirumand, this n minus k term in this is p to the power half n minus k minus 1. So this n minus k is can be replaced by d, and for a finite P group, this d is always less than or equal to n minus k. So in that sense, this bound is a refinement, and it's the proof is nothing but just uses a little bit trick, applying the same idea as obtained as given by Ellis and Vigold, who proved that mod mg is less than or equal to p to the power half d minus 1 into n plus k. So we just take it one step further to get that p to the power half d minus 1 into n plus k minus 2 plus 1. Okay, and as a corollary, this also improves the bound of Moravec given in terms of the co-class R. So we prove that mod mg is less than or equal to p to the power half r square minus r plus kr plus 1. So the Moravec's bound is p to the power r square plus k plus 2 into r. So r is instead of r square, we have half r square minus r, and instead of k plus 2r, we have kr plus 1. So in that way, it improves the bound in terms of the co-class and the order of the derived subgroup. Okay. Now, going further, we take into account the minimal number of generator of gamma 2g by gamma 3g. Okay. Why are we interested in that? We will let you know a little bit. So let G be a non-abelian P group of order P to the power n when mod gamma 2g equals to P to the power K and dg equals to D, and D of gamma 2g by gamma 3g equals to D2. Then one can see that mod mg is less than or equal to P to the power half D minus 1 into n plus K minus sigma going sigma d minus I, where I is going from 2 to the minimum of d and d2 plus 1. So you see the earlier bound, it gives you p to the power half d minus 1 into n plus k minus d minus 2. And here we are just going further. So we are interested in that because there is a problem by Berkovich and Janko. They have asked to determine the Schur multiplier of a special P group of rank 2. So the special P group of rank 2, we mean a group such that the derived subgroup, center, and the fraternity subgroup, that is GP into gamma 2G. They coincide and is isomorphic to ZP cross ZP. So here gamma 2G is generated by 2 elements. And this has been answered by Hatui in very recently. So you see, using our bound, we can find very compact bounds. I mean, not very far from each other, the lower and upper bounds. So the lower bound here is p to the power half d into d minus 1 minus 2. This is a standard result of Jones, and this is less than or equal to mod mg. And as a corollary, we can derive that here mod mg is less than or equal to p to the power half d into d minus 1 plus 3. So only 5 there, not many cases. Right? Going even one step further, you see that if G is a special P group of rank 3, so if D is greater than or equal to rank 3 and D greater than or equal to 4, so if D equals to 3 and if D equals to 3, then and G is a special P group of rank 3, then mod G is always P to the power x. So we can investigate that separately. So if G is a special P group of rank 3 and D greater than or equal to 4, then you see the lower bound is given by P to the power half D into D minus 1 minus 3 less than or equal to mod mg is less than or equal to P to the power half D into D minus 1 plus 6. So again, not very far from each other. If one wants to go further, maybe one can investigate this too. I'm not sure if anybody is interested in that. Anyway,
Pradeep, just a question. So, are these tightness of this upper bound and lower bound are kind of verified of these conjectures? I mean, these corollaries. I mean, for instance, equality for certain examples. Yeah.
For the special P groups of rank 2, yes, there are. Special P group of rank 3, I mean, I haven't investigated more. I mean, okay. I just have left it at that.
Yeah, but the general case is much more wide, right? I mean,
yeah, general case
upper.
Not, yes.
Yeah. So there is no hope. Yeah. Okay.
No. Okay. Also, whether mg is elementary abelian or not, we don't know. So we expect, I mean, not expect, we don't have any reasons to believe, but whatever special P groups which have been investigated, in all those cases, this mg has always been elementary abelian. So the extra special P groups, they were investigated by Blackburn and Evans, and then special P groups of rank 2 recently, and the special P group of maximum rank. So maximum rank in the sense that if the group G is generated by D elements, then mod gamma 2G is always less than or equal to P to the power half D into D minus 1. So if we take mod gamma 2G equals to P to the power half D into D minus 1, that is a special P group of maximum rank. So in all those 3 cases, mg is always elementary abelian. So the question is, I mean, is it true, at least for odd primes, that exponent of mg is always p for special P group G? Again, I don't have any reasons to believe it, and it might be easy to existence should not be that easy, perhaps. I'm not sure. Okay. So if that is, yeah. Okay. Okay. What else? Okay. Okay. So that was the bound in terms of the number of generators of the gamma 2G. Now, also one can consider the nilpotency class of the group G. No. Here is the proposition. Okay. So I wanted to shed some light on the proof. So here the proof is given by concentrating on the term x there, which I mentioned. That term x, one can see that is always the x I'm talking about, the kernel of lambda here. Here, the kernel of lambda, which appears here in the exact sequence and here in the denominator. Okay, so for this x, one can prove that this mod x greater than or equal to p to the power sigma d minus I equals to 2. I runs from 2 to minimum of d into d2 plus 1. And just incorporating this thing into a tricky manner to the exact sequences, one can derive this. Okay. So the problem is finding out a similar bound for x when group is of nilpotency class greater than 2. I don't know if one is interested in that. I mean, that's interesting to me at least. I mean, can a similar bound on x can be given in case of the high nilpotency class? Okay. So our refinement with respect to nilpotency class, again, investigating with x only, one can prove that this mod mg is less than or equal to half d minus 1 into n plus k minus this term, d minus I, where I runs from 2 to minimum of dc. And actually, one can go a step further, and this term, the rightmost term, the summation d minus I running from 2 to minimum of dc can be put here also. So one can join this thing and this thing together. So, but then this I shall run from 3 to minimum of d and c. Okay. So when either of d and c is 2, the bound coincides with the earlier ones. As both of these numbers grow, the bound becomes increasingly better. And again, applying the same idea, investigation about the x, since we know a good structure about the maximal group of maximal class, one can see that mod mg for a group, for a p group of maximal class, mod mg is always less than or equal to p to the power n minus n by 2. So as Moravec predicted, this is close to the square root of mod g. Okay, so I'll finish with stating an open problem for any specific problem, sub problem of the first problem I mentioned, that is the classification of groups with trivial Schur multiplier. So the co-class of finite p groups I already have defined. So it's an interesting result of Bettina Ike, who proved that for odd primes p, there are only finitely many p groups of co-class R, and mod mg less than or equal to s for every R and S. So if R and S are given, there are only finitely many p group of co-class R, such that mod mg less than or equal to s. So one can see that there are only finitely many p groups of co-class R with trivial Schur multiplier with this. So Bettina Ike in 2009 conjectured that In that case, the trivial Schur multiplier case, the order of the group can be bounded by a function of P and R. So if G is a finite P group for odd primes P and of co-class R with trivial Schur multiplier, then the order of G is bounded by P to the power F of R, where F is a function of R. This has been proved true by Bettina I for co-class 1, and for co-class 2, it has been proved by Newman in 2009. What about the bounds for the rank of Mg? So rank, so let's define this number. Sometimes this is defined as the rank of the group G. So this is the minimum number of, so this is the minimum number with which any subgroup of the group G can be generated. So this is maximum of D of H such that H is a subgroup of G. So it was conjectured by Jones and V. Gold in 60s that the rank of the Schur multiplier can be bounded by the rank of G, and they predicted that this should be bounded by a quadratic function of R. This was confirmed by Lubotsky and Mann, who proved that if G is any finite group whose Silo subgroups have ranks at most R, then D of Mg is this equal to I square plus log R to the base 2, the ceiling of this, plus I square. Moreover, if G is an odd group, this can be further improved. D of Mg is less than equal to I square plus the ceiling of I square log R to the base 2. And they also write in the paper that it still seems possible that this bound can be improved. I haven't seen any paper which have improved this bound since then. So at least I am not aware that this bound has been improved. Although their bounds for the exponent of the group G in terms of R have been improved, but not this one. Okay. Okay, I think this is the right time to finish my talk. Thank you.
Okay. Thank you, Pradeep. Anyone has any question? You can ask question if you have.
Pradeep, that conjecture by Bettina Ek just mentioned.
Yes.
So,
Yes.
what are the recent improvements on this? Are there
No,
after
no,
Bettina and
just what I gave, that it has been proved for co-class 1, for co-class 1 by Bettina Eich herself, and proved for co-class 2 by Newman. And since then, at least I am not aware that any progress has been done on this conjecture.
I see. But would you be able to say something? For example, if it's not trivial Schur multiplier, but let's say the order is very small. Let's say Schur multiplier is just order P. Something. Then still something. If it's some function of R still, or there are problems. So for some small co-class, maybe it is possible to derive such things. I don't know. I'm just asking.
I mean, I haven't given a thought to it. No.
Okay. And this Lubotsky and Mann's result, I think the first statement there is a mistake.
Oh, is it? Okay.
Oh, why you're writing R square, adding R square twice over there instead of writing 2R square?
Oh, that comes when the two groups comes into picture. That the prime 2 comes in the order, I think. No, that's right, I think. No, but why? Of course, why?
Yeah, I would write 2R square instead of writing it twice. Maybe that's another polynomial term or something. Yeah. Yeah, but this is also very old. I mean, there is no improvement. Yeah.
No,
it's very
no. There haven't been any.
Yeah, okay, thanks.
Any more questions? Okay, let's thank the speaker for wonderful talk.